Yes, this is the topic of the talk. So it's kind of in plain English, it's all about fine-tuning LLMs, computational methods for fine-tuning LLMs, and the trade-off is efficiency on the one side, computational efficiency, and the other is performance, right? Okay, so let's get started. So what is LLM fine-tuning? Most of you are, I'm sure, aware of this, but just for making things complete, let me give you like a walkthrough kind of an example, like a real world example, and then we get into the methods and so on and so forth, the math. Okay, so this is the LLM fine-tuning problem in like just real world terms. There's many popular LLMs today. I mean, Llama is one of them. There's DeepSeek, there's a Mistral, and so on and so forth. There's no shortage of the LLMs and several versions that are coming out. So the fine-tuning problem is as follows. These LLMs typically, as the name suggests, are very large. These are large language models. So sometimes they may have more than, say, 80 billion parameters, and sometimes they may have at least 7 to 10 billion parameters, at least on the other on the smaller end. So this is very large computationally for a typical client to deal with, but that's okay for really large institutions, the large companies, and so on and so forth. So for a usual client who is resource constrained computationally, for them to be able to personalize a general purpose LLM on a specific data set or specific task that they have on their device on the client side, one does some training. So basically initialize the model with the weights as given in the general purpose model, and then you try to update these general purpose weights for your specific task at hand and your specific data set at hand. The challenge is you cannot update all the 80 billion or I don't know, like billions of parameters because the client is constrained. So how do you update as less as possible? There's another name for these class of techniques. They call these PEFT methods. So that's parameter efficient fine-tuning methods. There are different classes of categories of solutions, but we'll look at it. Okay, these are several examples of real-world fine-tuned LLMs that were generated. For example, from Llama, because we were talking about Llama, but you can start with any major general-purpose LLM, and you want to fine-tune them efficiently for your specific use cases. For example, if I were to pick one, the Crystal 7 billion model, for example, was fine-tuned from the Llama 2 GPU. The K2 65 billion parameter model was fine-tuned from Llama 2, and so on and so forth. There's a whole directory of small LLMs and medium LLMs that have been generated by fine-tuning a general purpose LLM. Okay, so what are the classes of methods? This is one popular class of methods for fine-tuning in this context while maintaining parameter efficiency is the class of LoRA methods. LoRA refers to low rank adaptation, okay? And this picture is a 101 on LoRA, the classic naive or like the vanilla version of LoRA. This picture is taken from one of the tutorial books by Sebastian Rashka, who has many nice writings and teachings in his books. Okay, so on the left-hand side is regular fine-tuning. So you need to update the entire model. So you have some architecture around the weights. The pre-trained weights is what the model comes with. So these could be the Llama weights, for instance. And these could be, say, 80 billion parameters or some very large set of parameters in that weight matrix or the weight tensor. So you want to update that weight with a delta W in such a way so that it performs well on your personalized task and personalized data set. In the regular fine-tuning scenario, your delta W has as many parameters as your original pre-trained weight. So this is as large as your LLM, but the client cannot really do training of such a large model, right? So it's difficult. And on the right-hand side, you have the low-rank adaptation methods, where instead of updating the entire delta W, right, you have a factorized version of two matrices, which in the LoRA terminology, they are also referred to them as low-rank adapters. But these are basically two rectangular matrices, right? So tall and skinny kind of matrices based on the choice of rank or the number of columns. And so the total now, if you update the WB and WA, based to perform well in your personalized task. That leads to the task being doable, but as you see, the total number of parameters here is much smaller in comparison to what you have in regular fine tuning, right? And that's solely because of also depends on the choice of your rank for these adapters, okay? That's the starting point. I must also say that given the whole buzz around LLMs, there's a ton of research going on in on fine-tuning methods, as most of you are already potentially aware of. So the references that I would refer to in terms of the related work, you will see they're quite recent as well, because this thing has been evolving very rapidly on the academic side as well. Okay, so there is this method by Balazi et al. From just October 2024, so that's just a few months ago, not too long, called LoRA-XS, which also refers to LoRA extra small. This is another architectural improvement in terms of improving parameter efficiency. So instead of what you had in LoRA in the previous slide, which you see on the left, here there's another architectural fix where they introduce a third matrix and the R matrix, okay, which is a R by R square matrix, while your adapters B and A are rectangular, low rank matrices. Now in here, I'm color coding the right-hand side with blue in terms of those parts of the model which are frozen, so they're not changed. They're never updated during your training steps, during your optimization steps. While the only matrix that is updated is the small R by R matrix. So this leads to even further parameter efficiency in terms of the raw count of how many parameters need to be updated. Okay. So this is good. I mean, this is still in the right direction. But the primary improvement here comes from an architectural change of the model. Okay. But one thing this doesn't have a handle on explicitly, at least from a theoretical or algorithmic standpoint, is any guarantees on the performance of this model, right? You want this LoRA-XS to perform well in comparison to LoRA, for example, or closer to original regular complete fine-tuning, for instance, which is a nice gold standard to have. So along those lines, there has been newer methods, but let's be explicit a little more technically about some potential improvement points that one can focus on with respect to LoRA-XS. Firstly, the low-rank gradients are not the best approximation of the full fine-tuning gradient, right? So there's no guarantee that the low-rank gradients that you'd get with the LoRA-XS architectural updates would be good approximations of your gold standard, which is entire full fine-tuning of all the 80 plus billion parameters. Number two, the initialization of the frozen pieces, because R was the uninitialized piece, unfrozen piece, which you update, but B and A in LoRA-XS were frozen. So the direction of how you initialize these adapters may or may not be well aligned with the W naught that you're starting with, which is your general purpose pre-trained matrix weights, okay? Finally, the architecture is still dependent on some hyperparameters, which you'd like to achieve some independence with if possible, okay? So these are some good asks to have as we continue to develop these LoRA methods, as the community continues to develop these LoRA methods. So very soon, so that again around October 2024, very recently again, came this, let me reduce this window, this might be, okay, yeah, came this new method called LoRA Pro, okay, which has a better handle on performance, not just in terms of the parameter count or parameter efficiency. Okay, so pictorially, the architecture, as you see, that LoRA Pro deals with is not the LoRA-XS architecture. So there is no R matrix in the middle. It's just the B8. This is the classic LoRA architecture that you first saw, which is what you see on the left-hand side of the figure, the left-hand side figure. Now, on the right hand, so now you need to tune the adapters, B and A. They're not frozen anymore. Now, on the right-hand side, what you see is a high-level pictorial description of what guarantees the LoRA Pro methods tries to provide, okay? Basically, there is this gold standard, which I said is however your LoRA method is or architecture is designed and however you optimize it and initialize it and so on and so forth, you want ideally the LoRA gradients to be as close as possible to the full fine tuning, which is DL by DW, where W is the entire matrix, entire model, right? So if that was referred to or denoted by G, you'd like to have some updates uh, which result in some G tilde or equivalent G that is as close as possible to this full fine-tuning gradient. And the kind of equivalence these LoRa Pro people achieve is as follows. They show that this optimal G tilde, with respect to choice of Frobenius norm in terms of closeness, it actually lies in the subspace of the gradients GA and GB. Okay, so if you obtain the gradients of the A part of the adapter and the B part of the adapter, and if you look for a subspace around those gradients, that's where G tilde lies in. So there's an equivalence between an optimal G tilde and the functional form of how they can be represented using GA and GP. And now if you obtain GA and GB properly, because that again depends on how you initialize and how you optimize and how you choose your S and so on and so forth, then it is possible that if you do it properly, then you would end up in a G tilde, which is indeed optimally close to the full fine-tuning gradient. So you're now mimicking the full fine-tuning gradient as much as possible within the restrictions of this low rank search space. Okay, so that's LoRa Pro, okay, which is great. So the biggest improvement here is the fact that it's not just parameter efficient, but there's been some work done on optimality and improved performance, some handle on performance of these models. This is good. But one issue, though, is LoRa Pro is not as efficient as LoRA-XS, the extra small one, where B and A were frozen and you had an R by R matrix, just the R matrix in the middle, right? So that would be even more parameter efficient. So ideally, you want to have this kind of a result for LoRA-XS architecture, so that you not only are parameter efficient as much as possible, within these designs, but you're also performing optimally. So you want to push the performance as well. So that's one of our first papers along these lines that we did. We call this the LoRA Silver Bullet. And as far as the architecture goes, it's now, as you see on the left-hand side figure, we have the R matrix in the middle and B and A are frozen. So the blue are frozen. And so the only trainable part is the R by R matrix. So this is great. This is like the LoRA-XS. This is exactly the LoRA-XS architecture. But now the question is, how do you initialize B and A? And and if there is a functional form for GR or some sort of an equivalence between GR, the gradients with respect to the R, um, so that you can map back to some sort of an equivalent G tilde, here we refer to it by the G silver bullet tilde, so that ideally G tilde SB is as close as possible to the full fine-tuning gradient, G, which is if you were to update everything, right? You want that kind of a closeness. Again, we choose with respect to the Frobenius norm, at least our current results. Okay, so on the right-hand side, you see this 101 or like the zoomed up notion again. So what we show is that the initialization of adapters A and B in this architecture is extremely critical. If they were to not be initialized properly, you would end up making your updates within the subspace of equivalent gradients as shown in the LoRA-XS slide. So you'd be in this orange part of the subspace where black refers to the full fine-tuning gradient, which is what you'd like to mimic, but you'd be searching in a subspace due to a bad initialization of your A and B before you compute GR, that these would be much away from the full fine-tuning gradients at any round of optimization, right? So ideally, you want to initialize properly so that you end up in a subspace, say like the blue subspace, based on the equivalence map, um, so that your gradients are as close as possible within these constraints of these architectures and this model, with respect to the full fine-tuning gradient. That's what we'd like to achieve, right? So the question is, what is this magical initialization, or what is the right initialization, right? So that you are in the right space. So this at a high level, basically the results that follow are based on three kinds of maybe phenomena, right? Or three kinds of things. One is the existence of an equivalence map between the gradient of what you're updating, in this case GR, to some sort of equivalent gradient so that the equivalent gradient is as close as possible to the full fine-tuning gradient. So there's a question of equivalence that you like to figure out. There's a question of initialization of the adapters A and B. And of course, you're looking for some sort of optimality with respect to the norm that I mentioned. Okay, so in terms of the equivalence, I mean, the weights are basically the change in weights can be represented by this equation because that's how delta W was defined to start with, right? So delta W was SBRA, so the change in W depends on the change in R because the rest are frozen. This is trivial, though what you see in here outside the box, but that's a starting point. And then the first result is as follows. So the gradient with respect to R also has a similar functional form so that it gives you a G tilde, which is called the equivalent gradient. And now if you choose S, the scalar S, and then the adapters B and A properly, the right initialization, then you would have a G tilde, which is optimally close to the full fine-tuning gradient, okay? So it's a question of initialization at this point. We talked about the equivalent map that we showed, that the functional form looks like this, but initialization is critical now. That's the next question. And to recap this so far, these are the players or the actors that we're looking at. One is the full fine-tuning gradient. That's G. That's del by dou W. You have the LoRA extra small XS gradient, where your update of the gradient is with respect to the R matrix. That's the GR LoRA-XS. That's del by dou R, where L is the loss function, your machine learning loss or task loss, classification loss, so on and so forth. And you want to figure out a GR so that in the presence of this equivalence map that you see in the blue box, you want to figure out a GR so that it results in a G tilde such that the G tilde is as close as possible to your full fine-tuning gradient in the Frobenius norm. Okay, so that's what you want to look for. Okay, so it really depends on S, B, and A chosen properly. So that's where we are so far to recap and put everything together of where we came to. Okay, so what's the optimal solution going to look like, right? So the optimal solution to minimize this optimality gap under the presence of this equivalence map that we have happens to have this functional form. The proof strategy is actually not any fancy math, but more just first principles of minimizing this convex term and setting the derivative to 0 and substituting these equivalence results and sub-results that we have. Okay, so, and that ends up having this optimal form. The formula for GR happens to be of this form. If you were to minimize the closeness with respect to full fine-tuning, it needs to be in this form. It cannot be in a generic form of SBGRA, but it has to be the form where S happens to be 1 by S square. The B version of this functional form happens to be this matrix, and the A version happens to be this matrix, and you have GR, which is your LoRA-XS gradient in the middle, upon initializing A and B properly. Okay, so that's the functional form, but this still doesn't tell us how to initialize A and B properly. And secondly, there is this another scary business happening, as you see in two matrix inverses, and that's matrix inverses are not always our best friend in numerical linear algebra when you're talking about efficiency, although there's been some wonderful progress that has happened on this classic problem of just inverting optimally as much as possible, but this is still not the most efficient term that you like to have if you're solving for GR. But there's a good news. We will get there where we can somehow go away from this inverse. Okay. Okay, there's an equivalent sub-result. So when I say you set the derivative equal to 0 and solve for GR, and I said you also substitute some sub-results of equivalences. So just like you have G tilde equal to SBGRA, maybe just stare at this for a second, there's another equivalence result of a similar flavor, which happens to be this form where it looks exactly the same, except the fact that there's a transpose in here, and you're going from GR LoRA-XS in general with respect to G. Okay. While here you're looking in terms of the subspace G tilde's closeness to G, here looking at equivalence between GR and G, okay, without jumping from GR to G tilde directly. And you see this equivalence result ends up having transposes. The following is the proof. Again, the proof is for this result is again not fancy math, but the applying first principles of yeah calculus and linear algebra and so on and so forth. So to give you a quick flavor, we have these actors, right? G is for that proof of that sub result transposes, right? You have the del by del W, the loss with respect to the full. This is basically the full fine-tuning gradient, and this is the LoRA-XS gradient, del by dr. I mean, you just apply chain rule, you break it into two, the product of these two derivatives, and you can continue to do that. Further layer of chain rule by instead of looking at SBRA, you are just encoding RA as X, and you end up doing this, and you'd see that you'd have this equivalence result is true. Okay, so that's that. Okay, so now we have that the optimal solution has this formula or this functional form, right? That's by using the equivalence subresult in the previous slide and by setting the derivative of the loss to zero, this optimality loss to zero. So that's step one. You solve, set the derivative to zero and solve, and then you have the equivalence result that we proved so far, and then you get what we wanted, that the solution happens to be in this form. Okay, now the question is B and A, how do you initialize this? And then also this question of how do you initialize S, the scalar, and how do you somehow get around the inverse with respect to the efficiency issue? Okay. So now we had three problems originally with LoRA-XS, or rooms for improvement that we could do, and we figured out the first issue, which is in green now, not an issue anymore, that because LoRA-XS had LoRa gradients that were not necessarily best approximation of the full fine-tuning gradient, but we have figured out a way where there could be a best approximation through clever initialization and the existence of equivalence maps and optimalities, optimal solutions. Okay, now the other things that remain is how do you initialize, right? And the dependence on the hyperparameter S. Okay. So now we're getting to, I said the whole game is about equivalence optimum initialization. So now we're dealing with initialization. So that result happens to be as follows. All that matters is you perform one step of SGD full fine-tuning update, and then perform an SVD of that update and initialize your B, R, and A accordingly before you start doing applying the formula that I showed for the optimal gradient, right? So this is a paper, basically the title of the LoRA Silver Bullet paper, and there are others. This is quite recent as well, Feb 2025, so even more recent than LoRA Pro, obviously, because this was heavily inspired by LoRA-XS and LoRA Pro to deal with this issue. So computationally speaking, repeat what I said in terms of the initialization, what needs to be done is perform just one round of update of full fine-tuning. Of course, you could do on the entire data set at hand, but surprisingly, empirically speaking, we see that even when we used few samples, this tells something about sample efficiency of these updates and the behavior of these LLMs in general, which needs to be studied heavily, but that's out of the scope of what we studied in our paper. But even if you end up using just a few samples and get the full fine-tuning update for one round, and then we do the best rank approximation is given by the SVD, and we initialize our adapters A and B accordingly based on singular vectors and R accordingly based on singular values, scaled by a particular S that we need to figure out. So this is great. This happens to be the optimal initialization under the equivalence that we results that we showed, the equivalence maps, the functional forms. Now there's one other thing that remains, which is the third problem we had with to start with, which is how do you initialize S properly, right? What about S? Luckily, S also happens to vanish away, and so does the issue with the inverses, right? The inverses vanish away, the B transpose inverse and A transpose inverse, because these are singular vectors, they're orthonormal. So that's 101 linear algebra. And then what about S? We're in a very lucky situation where in the particular equivalence map that we care about, which is this one, where you initialize A and S in some form, and then you update for GR, and then so that you get the equivalent gradient that is as close as possible to the full fine-tuning gradient. In this scenario, S happens to vanish when you apply the formula that we derived for GR, which is the optimal GR that we had. Right, that special case. It doesn't vanish in the general case otherwise. So this is the proof for that. This was the formula, as if you can remember from a few slides ago. The optimal form for GR had this functional form. And when we apply the equivalence results that we have along with this formula, we end up seeing that S vanishes basically. And it doesn't vanish in the other case, which is not S independent. In our case, it ends up being S independent because things cancel out. Okay, because there's a S in here, and I mean, this is basic standard linear algebra properties that we had so far, and the equivalence maps. Okay, very good. We also show that the update direction that we proposed, the GR, the specific GR that I showed with the specific initializations that I showed, happen to provide an update to the loss function, which is always negative. So it's always loss is always reducing, basically, right? So your loss minus the updated loss, right? So this is loss minus updated loss. It's always negative in the right direction. It's always reducing, which is good. And of course, it depends on learning rate and so on and so forth, but at least in the right direction. It's in the reduction direction. Okay, so that solves the issues that we had with LoRA-XS, which lacked some theoretical understanding, which we provide in our LoRA Silver Bullet paper for this architecture, which gives us the benefits on not just parameter efficiency, but also on improvements in performance. So to summarize, this is very easy to apply because all you need to do is as follows. It's a silver bullet because it solves all the three problems that are highlighted in red. Those turn to green, right? So in one shot, all you need to do is follows. One round of full fine tuning, which you can, and then an SVD, but in practice we use a truncated SVD for speed again, because SVD is otherwise problematic. But since we do both of this on a small set of samples to start with, then what the natural samples that we have instead. And then we initialize A and B based on the SVD of the weight update that we get, the gradient update that we get there. And then once you do the SVD, and then we have the exact formula for GR, but that ends up canceling out because the initializations from the SVD for B and A are orthonormal, and S happens to cancel out in our particular map. So all you need to do is initialize it, the A and B as accordingly with that SVD, and keep updating your R as if you're just doing LoRA-XS, right? Because the rest magically cancel out implicitly. You don't have to mention it. And that gives you the optimal direction at any given round of optimization. So that's the theoretical guarantee and the practicality of it. And empirically speaking, we see this benefit. So LoRA Silver Bullet, for example, I mean, the paper has way more results, but for example, if you look at LoRA Silver Bullet with the Mistral 7 billion general purpose LLM, results on it, the number of parameters required for full fine-tuning of this particular model are 7 billion parameters, so that's very costly. We apply it on common sense reasoning benchmarks for the LLMs. We apply it on mathematical reasoning benchmarks and natural language generation benchmarks. So instead of updating 7 billion parameters, LoRA-SB just requires 0.23 million parameters if your rank was 32, or 2 million parameters, which is way smaller than 7 billion. And that's the same amount of efficiency that LoRA-XS also provides, but LoRA-XS doesn't have a handle on performance being optimal. While LoRA Silver Bullet, you see the performance is way better than LoRA-XS. Okay, and also our performance is way closer to full fine-tuning performance while maintaining the efficiency of LoRA-XS. So it's extremely efficient, but well-performing than current state-of-the-art models. And we see this trend again and again, basically, across our ablations with real-world benchmarks and real-world large language models. Okay, so that's that. This is on, well, so on and so forth. Other generative model tasks or LLM tasks, we see the similar trend. Even in terms of the loss function, the training loss that you visualize, as guaranteed by the theory, we see that right from the first round, the LoRA Silver Bullet loss is way lower than the LoRA-XS loss, right? Because LoRA Silver Bullet is supposed to be optimal at any given round. Um, and we see that in practice, as you see in these plots. Okay. And we also see that show that initialization is critical. So if you do a suboptimal initialization, you'd again not see the benefit as opposed to what we propose as the right initialization. Okay, the blue versus the red. And as a matter of practicality, this is quite easy to implement. We have our code available. You'll find it on GitHub, or you can always reach out to me, and I'll be happy to share the code. Okay, so then something else happened about maybe a couple days back or maybe a week back, which is this ABA class of methods that we introduced, which goes beyond the traditional LoRa variants we've seen so far. Here, what we try to do is follows. So let me just share this in a shorter version. The paper is of course online. So far the LoRa methods are just updating in some low rank subspaces, right? That's where the search is happening for fine tuning. But if you think about the W naught pre-trained matrix, there's no reason for that to be low rank. That's actually high rank, okay? So there's no reason that your search has to be low rank. The low rank was dictated due to the efficiency requirements. But if we can model low rank and high rank information in our updates, then there's a chance that you might perform even better than all the LoRa class of methods. But you also not only want to perform, you want to keep it efficient. So that's the challenge. Because if you take a traditional LoRa and put it together, then you'd end up in a high rank matrix, although your adapters are low rank. You lose the efficiency. And since you're searching in the low rank subspaces individually, so to get away from this problem, what we propose is this idea of using a Hadamard product. Okay, so now we have two pairs of adapters instead, A1B1 and A2B2, and it's a fact that even if A1B1 and A2B2 end up being low rank, the Hadamard product of this results in an overall matrix that is not necessarily low rank. It's certainly a higher rank. Okay, I wouldn't say it's the highest rank, but certainly higher rank. That's the direction, right? It depends on where you start with and what happens after the Hadamard product. It will be higher. Okay, so that's one way of modeling more high rank information while still maintaining the efficiency of LoRa style of methods when you're searching, because you're still searching smaller set of parameters. You can also, but you have more adapters, right? Because of the product on the left and right hand side, right, of the Hadamard product, the adapters on both sides. But you can also split your rank, right? So if you had R being the rank that you chose in a traditional LoRa setting, here you can split that as R by 2 and R by 2, for instance. And then overall, you're still same level of parameter efficiency, but you're modeling high rank. You're expressing more, right? You're expressing more information. You're expressing higher rank information, which is good for learning. So in the beginning, we do synthetic results and then we do real results and benchmarks. In synthetic results, we started looking at specific structures of matrices. What if your W naught was orthogonal, or what if it was low rank indeed, and if it was sparse or random, and so on and so forth. In all our simulations, we see that this method with the Hadamard that we call ABA, because it's AB and times BA basically. The ABA method has a better reconstruction error than any of these LoRa methods, right? So that's good. We see that in approximations of the visualization of the loss landscape as well. So that's great. But now the question is what happens in real benchmarks, right? In terms of real benchmarks, we again show that the ABA class of method outperforms the LoRa class of methods because we're able to express better on various tasks. And in terms of efficiency, we show that we maintain similar efficiency as LoRa in terms of, say, the memory footprint and so on and so forth. And internally, I will just note that There's some numerical tricks of how you deal with the Hadamard product in terms of maintaining good memory efficiency, because now you have double the number of adapters, your memory would increase if you don't use these tricks. The internal numerical tricks is an equivalence between Hadamard products and what is known as the very famous Khatri-Rao product. Okay, if you use that equivalent version of expressing Hadamard products using Khatri-Rao products, then you have memory efficiency gains as well. Memory efficiency, I wouldn't say gains, you would maintain memory efficiency, which would not blow up. Um, yeah. Okay, so there's that. That's the shorter version of the more recent work on ABBA. And then comes the question of how do you fine tune in the federated setting, right? So far we were looking at one client at a time where you're fine tuning a pre-trained model to perform well on your own task in an efficient way in your personalized setting. But what if you had multiple clients, right? Where each client has their own data set that they don't want to share and they want to fine tune together as a group. You want to get the wisdom of the crowd of all the clients as opposed to individual clients fine tuning on their own data sets. You want to get a federated version of the model which performs way better as a whole than any other individual LLM fine tune method. So pre-LLMs, this was the traditional federated learning kind of a workflow vanilla version where you have a bunch of clients, they have their own data, each client trains the entire model. You upload the entire model to the server does a weighted aggregation of that model, which is the aggregated model. It's basically a way to put together, ensemble the wisdom of the individual models into an averaged aggregate model, and that's sent back, and this rounds of forward and back prop continue, right? So that's traditional FL. But as you clearly see, this is extremely impractical in the post LLM world, or like once LLM kind of thing happened, this is almost impractical to do this because there's no way you can have these small client computer resource constrained clients to train an entire ChatGPT or entire DeepSeek or Llama or Mistral, you know? So you want these clients to instead do fine tuning, right? And also do efficient fine tuning and the right aggregation so that your federated model performs well. Okay, so the setup in the LLM era is little different than the previous slide. So here what happens is the training doesn't begin with the client. The training is done with the large companies or large universities or organizations or rich countries, so on and so forth, that generate these large models. Large language models are downloaded by the clients and some update, doesn't have a linear update as I show in this right-hand slide, but some update needs to be done that needs to be gathered properly at the server. So this is the systems interactions of who is communicating what in the LLM world for doing federated LLM fine tuning. Okay, so what is this? What is existing currently? The current methods do the follows. Each client performs a standard LoRA update, which is of this kind of form, right? This could be LoRA or LoRA Silver Bullet, whatever your favorite LoRA is. For now, LoRA Silver Bullet is great. You could also do ABBA, for example. But say if you're sticking to the LoRA class of methods and you did LoRA update, what the current methods do is the clients share the adapters, B1 A1 from the first client, and BM AM from the mth client, right? The adapters go to the server. And the server averages currently, the current methods, the server for federated learning with in the fine-tuned LLM setting, the server averages the adapter separately and then does a product and then does an overall LoRa style update. It's to give you the aggregated model, which all the clients again download, and this kind of rounds continue, right? Individual local training followed by federated aggregation, so on and so forth. But there's an elephant in the room here. So this is the same thing that I mentioned in pictures. So, but there's an elephant in the room here. Clearly, this is kind of a high school kind of an observation, right? Which is the product of averages of matrices is not the same as the average of the product of the matrices, right? But ideally, what you want is what's on the right-hand side. That's the federated learning. The left-hand side is not federated learning in the optimal sense or in the traditional sense, right? So how do you fix this? But there's an issue. It's not that the people who are aggregating the way they're aggregating on the left-hand side don't know about this, but there's an issue, right? They're not doing the right-hand side kind of aggregation because as soon as you multiply the adapters, you're in the high rank setting again, you're losing parameter efficiency, right? You want to keep it efficient and still be able to obtain this right-hand side part of an aggregate, right? That's the reason it's happening, not that it was not observed, because it's very simple to observe this. And methods that currently do this include the methods of federated fine-tuning called FedIT and so on and so forth, which are existing papers. So we fix this in a very simple way, actually, where what we do is the server not just does individual averages of the adapters, but also measures this gap, the gap that should not be existing, right? The gap between the average of the products of adapters minus the product of the average of the adapters, and that's the gap that shouldn't be existing. We pass that. That's an increase in communication cost. We pass that back to the clients, and we have a correction update that we do on the client so that overall you get an exact aggregation. So that's why you call it FedEx or federated exact LoRA, because this exactness was missing. And this is a simple fix, way simpler fix than what you saw in terms of all the theory in the papers that we did for ABBA and LoRA Silver Bullet. This is a much simpler paper. This got accepted by ACL main conference maybe a week or so, a few days back for 2025. Okay, so that's that. This is what I just said in writing. So this results in exact aggregation, and we see the benefits are also quite considerably better with respect to existing federated LLM fine-tuning methods such as FedIT or FFA LoRA, right? Our performance is way closer to centralized performance due to just this exactness fix. Okay. And we also then did an ablation where the training is happening using differential private privacy preserving optimizations, optimizers such as DPSGD. And then we see that LoRA Silver Bullet based federated exact aggregation, when also done, where the updates are also done with differential privacy, end up in resulting in a much better privacy utility trade-off for different values of the privacy parameter epsilon. Lower epsilon is higher differential privacy, right? Whereas higher epsilon. But we see that we have a way better efficiency performance as well as privacy trade-off with existing federated methods over our federated silver bullet method, which is LoRA Silver Bullet based federated LLM fine tuning with exact aggregation. Okay, everything put together with differential privacy. Okay, so this is what I said in pictures again, in writing again. And we see similar things, similar improvements across different ablations and data sets and so on and so forth. Okay. To conclude, I would also like to mention, just like federated learning, there was a variant of such collaborative or distributed learning called split learning, where there's another level of model parallelism. The entire model is not being trained on each device, but partial of the model lies in the client, partial model lies in the server. In this kind of a setting, before LLMs, there was a lot of progress that was done. This leads to some more efficiency in terms of compute and communication for the client. But the question is, what can be done at the intersection of split learning and LLM fine-tuning? Because now we're living in a world where LLMs have been developed, which was not the case when FL and SL were originally introduced, right? So this opens doors to a new set of problems where there's some applied stuff that's been done, but more theoretical and algorithmically motivated stuff needs to be done here in this kind of a setting where we have better performance gains guaranteed, and we see that in reality. So that's a closing slide, and there's a bit of a philosophical slide, right? So what you see on the left is how people were communicating just a few decades back. If someone were to make an international call, you call in a telephone exchange, they switch a bunch of wires and a lot of routing. It takes a while. It's very costly. Right now, after the ICT revolution, we have seamless communication and at a very cheap rate, and we take this for granted. But we're living in a world where data is being generated rapidly and being siloed, and we cannot put it together at one place because of privacy and regulatory constraints. So this opens problems of how to perform collaborative and decentralized AI in an efficient way so that collaboration happens seamless by default. So that's the future we want to head towards. That opens door to many, many problems and projects that one could do in order to achieve that dream. Okay, so let me conclude there. And I'm open, so we have 10 more minutes, I believe, and I'm totally open to questions. And feel free to reach out to me as well if you'd like to discuss more. offline and schedule a meeting later on, or if you need code for any of these methods. All of this code is actually on GitHub. I can point you to resources.